We have confirmed the existence of over 5,500 planets outside our solar system. Most of them are hellscapes, burning gas giants, frozen rocks, worlds with iron rain, and winds that move faster than sound. Places where nothing we understand as life could survive for a single second. But some of them are different. Some of them are suspicious. Today, we're going to look at 10 real planets, confirmed, documented, studied, that scientists believe could actually support life. Not life as science fiction imagines it. Life in the real sense. Liquid water, stable temperatures, a protective atmosphere, the conditions that allowed something to crawl out of the ocean on Earth 400 million years ago, and eventually look up at the sky and wonder what's out there. Some of these worlds are remarkably similar to Earth. Some are so different that life there would look nothing like anything we've ever seen. And at least one of them may not be waiting for life to begin. It may have already started. Let's go through them one by one. On January 6th, 2015, NASA's Kepler mission confirmed the existence of a planet that quietly topped every ranking system scientists use to measure habitability. Kepler 442b sits 1,200 light-years away in the constellation Lyra. It is 1.34 times the size of Earth, close enough to almost certainly be rocky rather than gaseous. It orbits its star every 112 days, sitting comfortably within the habitable zone, receiving about 70% of the solar energy Earth gets from the sun. Not too much, not too little. On the Earth Similarity Index, a scale from 0 to 1, where 1 means identical to Earth, Kepler 442b scores 0.84. For comparison, Mars scores 0.64. Venus, despite being our closest neighbor, scores just 0.44 because of its crushing atmosphere and 465-degree surface temperatures. Kepler 442b scores higher than any other confirmed planet we've ever found. But here's where it gets interesting. Its host star is a K-type orange dwarf, slightly smaller and cooler than our Sun, but more stable. K-type stars live for 15 to 30 billion years, compared to our Sun's 10 billion. If life on Kepler 442b follows a similar timeline to Earth, it has had, and will continue to have, far more time to evolve complexity than we ever will. The problem, as always, is what we can't see. We don't know if it has an atmosphere. We don't know its surface composition. We can't measure whether it has liquid water. We know its size, its orbit, and its star. Everything else is inference. But on paper, right now, Kepler 442e is the closest thing to another Earth we have ever confirmed exists. 14 light-years away. That's the distance to Wolf 1061c. In cosmic terms, that is essentially next door. The Milky Way is 100,000 light-years across. Our nearest stellar neighbor, Proxima Centauri, is 4.2 light-years away. Wolf 1061c, at 14 light-years, is among the closest known potentially habitable planets to Earth. Discovered in 2015, it orbits a red dwarf star and sits within the inner edge of the habitable zone, meaning it receives slightly more stellar energy than Earth. Enough to be warm, possibly enough to be too warm, depending entirely on its atmosphere. Its mass is at least 4.3 times Earth's, placing it in the category called super-Earths. And this is where things get complicated. Super-Earths exist in a frustrating gray zone. If Wolf 1061c is mostly rocky, the higher gravity would produce a thicker, denser atmosphere, potentially rich enough in greenhouse gases to maintain liquid water, even if it's slightly farther from its star than ideal. The stronger gravity would also help it hold on to that atmosphere for billions of years, resisting the stellar wind that slowly strips away lighter planets. But if it's too massive, the atmospheric pressure at the surface could be crushing. If it accumulated too much hydrogen during formation, it might be a mini Neptune with no solid surface at all. We genuinely don't know. What makes Wolf 1061c particularly valuable isn't just its potential habitability, it's its distance. At 14 light-years, it's close enough that future telescopes, ones being planned and built right now, may be able to directly image its atmosphere and determine its composition, not in a century, potentially within decades. Wolf 1061c might be the first planet beyond our solar system where we can look and actually say, Yes, there is oxygen there. Or, no, it's just carbon dioxide. The tools to answer that question are almost within our reach. On April 17, 2014, astronomer Elisa Quintana stood before a room of journalists and announced something that changed how scientists think about life in the universe. The Kepler Space Telescope had found a planet 582 light-years away in the constellation Cygnus that was almost exactly Earth's size, 1.1 times our radius, orbiting in the habitable zone of its star. This was Kepler 186f, and it was the first time in human history we had confirmed that Earth-sized worlds exist in regions where liquid water could theoretically flow. But here's the strange part. The star it orbits is an M-type red dwarf, and Kepler 186f sits at the outer edge of that star's habitable zone, receiving only 32% of the stellar energy Earth gets from the sun. By the most basic calculations, it should be a frozen world, permanently glaciated, a planet where the ocean's never liquid, where the temperatures never rise above the point where ice melts. And yet, if Kepler 186f has an atmosphere with greenhouse gases, carbon dioxide, methane, even just a modest amount, that 32% of solar energy might be enough. The greenhouse effect, the same mechanism warming our own planet right now, could trap enough heat to keep the surface liquid. A world that looks frozen from the outside could be temperate on the inside. Think about what that actually means for the rest of the galaxy. Red dwarf stars are not rare. They are the most common type of star in existence, making up roughly 70% of all stars in the Milky Way. If Earth-sized planets in the habitable zones of red dwarfs can support liquid water despite receiving a fraction of our sunlight, then the number of potentially habitable worlds in our galaxy doesn't need to be counted in millions. It needs to be counted in billions. Kepler 186f showed us that the universe's most common stars can host the right kind of planets. We just need those planets to have the right kind of air. On January 6, 2020, at the 235th meeting of the American Astronomical Society, astronomer Emily Gilbert announced a discovery that had a particular quality the others lacked. It was close. TOI 700d is 101 light-years from Earth. That's still an almost incomprehensible distance. Traveling at the speed of the fastest spacecraft ever launched, it would take over 1 million years to reach it. But in the catalog of potentially habitable exoplanets, 101 light-years is nearby. Close enough to study in detail, close enough to point the James Webb Space Telescope at and actually learn something. The planet itself is 1.1 times Earth's radius, orbiting in the habitable zone of a stable red dwarf star. It receives about 86% of the stellar energy Earth gets from the sun, completing one orbit every 37 days. And then, in January 2023, something unexpected happened. The James Webb Space Telescope turned its instruments toward TOI 700d and detected what appeared to be signs of an atmosphere. The data was preliminary. Scientists were careful to call it possible signs, not confirmed signs, but the signal was there. Something surrounding this planet, something between its surface and space. An atmosphere changes everything. Without one, a planet is just a rock. With one, it becomes a candidate. Pressure, temperature regulation, protection from radiation, the possibility of weather, of liquid water cycling between surface and cloud, of chemistry complex enough to eventually produce something that reproduces itself. The James Webb data is still being analyzed. Follow-up observations are scheduled. TOI 700d has not been confirmed as habitable, but it has become one of the highest priority targets for atmospheric study in the entire field of exoplanet science. And when we finally get a clear answer about what's in that atmosphere, whatever we find will tell us something profound about how common or how rare worlds like ours actually are. On August 24, 2016, astronomer Guillaume Anglada Escudé announced the discovery that turned interstellar travel from a distant fantasy into an engineering problem with a specific destination. Our nearest stellar neighbor, Proxima Centauri, just 4.24 light-years away, has a rocky planet orbiting in its habitable zone, 4.24 light-years. That's 40 trillion kilometers. It's the equivalent of driving around Earth 1 billion times. And yet, by the standards of interstellar space, it is essentially in our backyard. Proxima Centauri b receives about 65% of the energy Earth gets from the Sun, orbits its star every 11.2 days, and has a mass at least 1.07 times Earth's. On paper, it fits the profile. But here's where everything breaks down. Proxima Centauri is one of the most violent stars in our stellar neighborhood. It regularly produces flares, sudden bursts of X-ray and ultraviolet radiation, tens of thousands of times more powerful than the largest solar flares ever recorded on our Sun. These flares bombard Proxima b at a rate and intensity that, on Earth, would strip the ozone layer and sterilize the surface within years. The planet almost certainly has no magnetic field strong enough to protect it. It's likely tidally locked, one face permanently toward the star, baking in radiation, the other permanently in frozen darkness. The stellar wind pressure it experiences is roughly 2,000 times what Earth endures from our own Sun. And yet, some researchers argue that life, if it arose on Proxima b, would not develop on the surface at all. It would develop underground, beneath rock and soil thick enough to block radiation, or in deep ocean environments, far below a surface layer of sterilized water, shielded by hundreds of meters of ocean above it. Life on Earth spent its first 2 billion years entirely in the ocean, protected from a young sun that was itself far more active and violent than today. Life doesn't need perfect conditions. It needs a foothold, a place where chemistry can get complicated enough, stable enough, for long enough. Whether Proxima b offers that foothold is one of the most urgent questions in science. And it's the one question, above all others, where the answer is close enough to maybe reach within a human lifetime. In April 2024, astronomer Charles Cadieux at the University of Montreal published findings that transformed a planet discovered 7 years earlier from an interesting candidate into one of the most compelling targets in the search for life. LHS1140 b orbits a red dwarf star 49 light-years away. It is 1.7 times Earth's radius and 6 times Earth's mass. The James Webb Space Telescope had analyzed its atmosphere and detected what appeared to be a nitrogen-rich chemical signature, the first potential detection of a nitrogen-dominated atmosphere around a rocky world in the habitable zone of another star. Nitrogen is not exotic. Earth's atmosphere is 78% nitrogen. It doesn't react easily with other chemicals. It doesn't burn. It doesn't freeze at normal temperatures. It is, in many ways, the ideal atmospheric filler, a stable, inert background gas that creates pressure without causing problems. A nitrogen-rich atmosphere on LHS 1140b would suggest something remarkable, that this planet may have held onto a stable, Earth-like gaseous envelope for billions of years. But here's what makes LHS1140b genuinely unusual. That 6 times Earth mass creates significantly stronger gravity, about 1.3 times Earth's pull. Walking on this world would feel like carrying a 30-kilogram backpack everywhere you went. Every step, every movement. Constant, relentless. But that same gravity works as a shield. Earth is slowly losing its atmosphere to space. Solar wind strips away lighter molecules. While Earth may have 1 to 2 billion years of comfortable habitability left before our aging sun makes the surface hostile, LHS1140b may maintain stable conditions for 5 billion additional years. Its star, a calm, stable red dwarf, will continue burning steadily for trillions of years. Not billions, trillions. A timescale so large that our sun's entire lifespan looks like a brief flicker by comparison. If life exists on LHS 1140b and follows an evolutionary timeline similar to Earth's, it has had billions of additional years to develop complexity, and billions more ahead of it still. We may be looking at a world where life is not just possible. We may be looking at a world where life has had more time to evolve than we can meaningfully imagine. On February 22, 2017, astronomer Michael Gillen announced a discovery that rewrote the textbook on what a planetary system can look like. 40 light-years away, in the constellation Aquarius, 7 Earth-sized planets orbit a single ultra-cool dwarf star called TRAPPIST-1, all of them Earth-sized, 3 of them in the habitable zone. The entire system is so compact that all 7 planets fit within the orbital distance of Mercury around our Sun. If you lived on any of these worlds, you would see the neighboring planets not as points of light, but as visible disks in the sky, larger than our moon appears to us. You could watch them move, watch them transit the star, watch each other's weather systems if you had a powerful enough telescope. The 4th planet from the star, TRAPPIST-1e, is the one scientists keep coming back to. It is 0.92 times Earth's radius, 0.69 times Earth's mass. It receives 66% of the stellar energy we get from the Sun. Its density suggests a rocky composition, possibly with a thin atmosphere. On every measurable dimension, it is the most Earth-like world in terms of size and composition ever confirmed. And then there is the age. TRAPPIST-1, the star, is 7.6 billion years old. Our own Sun is 4.6 billion. The difference is 3 billion years. If life on TRAPPIST-1e arose at the same rate it did on Earth and followed a similar evolutionary timeline, then when it reached the equivalent of our current technological level, the Earth was still a ball of molten rock with no solid crust. Complex multicellular life hadn't appeared here yet. Photosynthesis hadn't been invented. 3 billion additional years of evolution. 3 billion years of time for complexity to build on complexity, for intelligence, if it arose, to develop and advance and reach levels we have no framework to imagine. In September 2023, the James Webb Space Telescope detected possible signs of atmospheric chemistry on some TRAPPIST-1 planets. The scientific debate about the interpretation continues, but the system remains the single most studied multi-planet habitable zone system we know of. And the more we look, the more interesting it gets. On July 23, 2015, NASA held a press conference and used a phrase that traveled around the world by end of day. Earth 2.0, Kepler 452, is 1,400 light-years away in the constellation Cygnus. Its host star is a G2 type star, the exact same spectral classification as our Sun, burning at nearly the same temperature, emitting nearly the same kind of light. The planet orbits that star every 385 days, compared to Earth's 365. It sits at 1.04 astronomical units from its star, almost exactly Earth's orbital distance. It receives about 10% more stellar energy than we do. On almost every dimension that matters, this looks like Earth orbiting a sun. But the detail that makes Kepler 452 genuinely unsettling is not how similar it is. It's how much older. The host star is 6 billion years old. Our Sun is 4.6 billion. The difference is 1.5 billion years. If life arose on Kepler 452b when the planet was roughly the same age Earth was when life appeared here, then that life has had an extra 1.5 billion years to evolve. Consider what happened on Earth in the last 500 million years. The Cambrian explosion, the colonization of land, the rise of dinosaurs, their extinction, the emergence of mammals, the appearance of our species, the entirety of human civilization. All of it fits inside 500 million years. And we're talking about an advantage of 1.5 billion. What does intelligence look like with 3 times as much time to develop? What technologies exist? What understanding of physics, of biology, of the universe? The gap between us and potential life on Kepler 452b, if it exists, would not be measured in centuries. It would be measured in geological epochs. The planet's radius is 1.5 to 1.6 times Earth's, placing it at the uncertain boundary between rocky, super-Earth, and gaseous mini-Neptune. We don't know its composition, but we know its star will remain stable for billions of years more, offering a total habitable window potentially twice as long as Earth's entire history. If something is there, it has had time to become something extraordinary. On November 21, 2011, astronomer Guillaume Anglada-Escudé announced the discovery of something that sounds like it was invented for a science fiction novel. Just 24 light-years away, close enough that, in the distant future, it might be a realistic destination. A planet 4.5 times Earth's mass orbits in the habitable zone of a red dwarf star. That alone would be interesting. But this star is part of a triple star system. From the surface of Gliese 667 cc, you would look up and see 3 suns, not 3 dots of light. 3 actual suns, 2 of them, a pair of orange dwarf stars orbiting each other, would appear as bright objects in the sky, visible even in the daytime as distinct disks. The third, the red dwarf the planet actually orbits, would be the one directly overhead. The sky would never be completely dark. At certain times, the planet would have 3 simultaneous sunsets. Now think about what that actually means for life. Gliese 667 cc is almost certainly tidally locked to its red dwarf host. One face permanently toward the star, one face permanently in darkness. Between them, a band of permanent twilight, the terminator zone, where temperatures might be stable enough for liquid water. And here's the detail that makes this planet genuinely interesting, rather than just visually spectacular. It receives approximately 90% of the stellar energy Earth gets from the sun. Not from 3 stars combined, just from its red dwarf host. The 2 orange dwarfs are far enough away to add only ambient light, not significant heat. But that 90% figure, combined with the stability of a tidally locked terminator zone, suggests that liquid water is entirely plausible. The terminator zone of a tidally locked planet has a quality that Earth can never offer. Stability. Earth's climate swings. We have ice ages, warming periods, seasonal variations, weather driven by our axial tilt and elliptical orbit. The terminator zone of Gliese 667 cc would maintain approximately the same temperature, the same light level, the same conditions for billions of years. No seasons, no ice ages, constant. Life on Earth took billions of years to gain a foothold, partly because the environment kept changing. A stable environment might accelerate that timeline considerably. 3 suns in the sky, eternal twilight. And perhaps, in that permanent dusk, something has been waiting long enough to look up and wonder what those bright objects actually are. On September 11th, 2023, astronomer Nikku Madhusudan at the University of Cambridge published findings that sent a visible wave of tension through the astronomical community. The James Webb Space Telescope had analyzed the atmosphere of K218b, a planet 124 light-years away, and detected a molecular signature consistent with dimethyl sulfide. On Earth, dimethyl sulfide is produced by one source and one source only: biology. Specifically, by marine phytoplankton, microscopic ocean organisms that form the base of the ocean food chain. No known geological process, no known non-biological chemical reaction produces dimethyl sulfide in significant quantities. Every time we detect it in Earth's atmosphere, it is a sign of life. Now it has appeared, tentatively, in the atmosphere of another world. The scientific community's response was measured and careful, as it should be. A single detection from a single telescope is not confirmation. There may be unknown abiotic chemistry that produces dimethyl sulfide in hydrogen-rich atmospheres we've never encountered before. The signal could be a misidentification. The analysis could contain errors. The entire field of atmospheric detection at this scale is new enough that the tools are still being calibrated. But the signal is there, and it hasn't gone away under repeated analysis. K2-18b is a strange world. It is 2.6 times Earth's radius and 8.7 times Earth's mass, a class of planet called a Hycean world, meaning it likely has a hydrogen-rich atmosphere over a global ocean. Not a rocky world like Earth. A water world with a thick, exotic sky. Surface temperatures might hover around 20 degrees Celsius, warm enough for liquid water, but the atmospheric pressure would be many times what we experience at sea level. The sky would be heavy and pale. The light from the star, filtered through that thick atmosphere, would be dim and reddish. Life there, if it exists, would be unlike anything we have ever imagined. Not creatures on a surface, because there may be no solid surface. Life in a global ocean, perhaps photosynthesizing under a dim sun filtered through kilometers of hydrogen atmosphere. Perhaps chemosynthetic, feeding on chemical gradients in the deep water. Follow-up observations are scheduled. Independent analyses are underway. Within the next few years, we may have a clearer answer. But here is the truth that is difficult to sit with calmly. We have found a planet with liquid water, temperatures compatible with life, and a chemical signature in its atmosphere that, on the only world where we know life exists, is produced exclusively by living organisms. We have not confirmed life beyond Earth, but we may be closer than we have ever been to having to seriously consider the possibility. 10 planets. 10 different ways the universe might have figured out how to do what it did here. And these are only the ones we've found so far, with telescopes that are still young, pointed at a tiny fraction of the sky, capable of detecting only the largest signals from only the nearest stars. The full catalog of what's out there is something we haven't even begun to read. The question of whether life exists beyond Earth is sometimes treated as philosophical, abstract, something we may never actually answer. But look at what we found in just the last 30 years. In 1992, we had confirmed exactly 0 planets outside our solar system. 0. Today we have over 5,500 confirmed, with thousands more candidates waiting. We have found planets in the habitable zones of the most common stars in the galaxy. We have found planets with atmospheres. We have found a molecule that life makes, in the atmosphere of a world with liquid water. We are not searching blindly anymore. We are narrowing in, and somewhere out there, on a world orbiting a dim red star, or bathed in the light of 3 suns, or drifting through the permanent twilight of a tidally locked horizon, something may have already found us in its own night sky. A faint yellow star, unremarkable, one of hundreds of billions, and wondered exactly what we wonder now.